guys are going to have a weird cutoff at the beginning. That's okay. Embrace the jank. Okay, so this will classify families of line bundles. Okay, cool. So with that in mind, let's get to the first section. So I'm going to call this rigidification, which is associated with the previous kind of rigidity we talked about, although it's a little different. And Picard functors. First foray, if you will. With that, I'm going to move down a bit. Okay. So in order to make our above strategy work, we're going to need to put a few hypotheses on X. And in order to understand what kind of hypotheses we want, I'm not going to explicitly spell out why each thing does what it does, but the important thing to remember, right, is that so whenever, and this is a thing throughout a lot of geometry, whenever we think about families of geometric objects, automorphisms of those objects become things that we need to pay careful attention to. Right? So they demand careful attention. And in particular, if we're going to build some kind of moduli space or thing of that type that classifies them, then if you have to worry about automorphisms and so on, then you're led to basically having to think about stacks. And stacks I think are a fairly intuitive notion, but here I don't want to have to go through the technical details involved. So in order to avoid that, so I guess to avoid this, we will impose rigidity constraints to eliminate automorphisms. And this is, again, a common way of doing things in these kinds of problems. If you're doing something like homotopy theory and you take your homotopy, or you quotient out by homotopy equivalence, for example, then that can be viewed as an analog of sort of getting rid of automorphism type data. It's not quite the same, but if you've done a bit of basic algebraic topology, then that should hopefully provide some intuition. Okay, so another thing I'll say is that, let me see this. So as such, let's have our case scheme X be what? Well, for one, it's going to be proper. Make this a bit even. We want it to be geometrically connected. And we want it to be geometrically reduced. So, these conditions make it so that the sheaf cohomology of the structure sheaf is rather nicely behaved. For example, our cohomology groups are going to be finite dimensional as k-vector spaces, and we'll be able to say something specific about them. Also, for I guess I'll say for ease of representability. Representability. What a mouthful. Okay. So we assume that the set of k rational points of x is not empty, and we'll put something in there. Let's call it E. And the choice of the name E here is suggestive because where we're hoping to apply this theory is of course to abelian varieties, and for an abelian variety, the assumption that we have this k rational point is harmless because this is provided by the identity. So basically, all of this theory can be done without assuming that we have a k rational point, and for more general settings you need that, and Growth and Deke actually goes through that construction in a lot of detail, so you can check the notes for references, but for our purposes this will suffice. Okay, so our scheme X is a k scheme, so it has a structure morphism, so let's let F from X to spec K be the structure morphism. And please stop me if you have any questions. Just want to remind you guys. Okay, let's have T be a k scheme. And I already said that E is our distinguished k rational point. Okay, so then we get ET, I'll call it, which is a T rational point of X, but base change to T. And how is it obtained? Well, it's a section of FT, right? So we can base change the structure morphism to get it going from X base change to T. And where does this section come from? Well, it's induced by pullback. So there's a big commutative diagram you can write down, and the induced map is this ET. Okay. So why do we care about this guy? Well, this plays into the notion of rigidity, right? So again, I'm just going to keep the notation of T and E. Okay, so define, this will be a script R. Okay, that didn't turn out so poorly. That's good. T X over K E. This is my own notation. It's not standard or anything like that. R here is for rigidity, if you're curious. So to be the category of what? Well, it's going to consist of what are called rigidified line bundles. On XT. So what are these things? So maybe I should underline rigidified line bundles. So these are pairs, or it's the category of pairs rather, Li with L a line bundle over XT, and iota, I guess it said I, it should be an iota, a rigidification. Rigidification. So what is a rigidification? Well, rigidification is an isomorphism to the trivial line bundle of what? Well, what we do is we take our line bundle L, and we pull it back by our induced section. Hold on. Do this. It's L, it's E, T, pull back. Okay, cool. So that's what the morphisms look like in our category. And that's what the objects look like. What do the morphisms look like? Well, a morphism sorry about that. Okay, a morphism is theta, which goes from a pair lambda iota to a pair lambda prime iota prime. maybe I should say with. So theta, a map from L to L prime, a morphism of sheaves, right? Sheaves defined over xt. And, well, we have a commutative diagram. So again, we have two rigidifications, right? So we have the pullback of L and of L prime. These are mapping down to the trivial line bundle, again, by iota and iota prime. And then what appears here, well, it's the map induced by the pullback. And actually, let me think for a second. Have I flipped things here? I don't think I have. If I have, it doesn't matter. Just reverse it and nothing will change. Because ultimately we'll care about isomorphisms and the direction shouldn't really matter. Okay. And of course we want this to commute. It's hopefully obvious, but I'll say it. Okay. So where does the notion of family of line bundle come in here, right? Well, we're talking about line bundles on X sub t, right? Which is the same thing, if you will, as X crossed over K with T, which you should think of as a family of line bundles parameterized by T, right? Line bundles on X. Or well, sorry, family of line bundles on X parameterized by T. So basically, for every choice of parameterizing space T, we're building up a separate category that thinks about line bundles of that type. And in order to eliminate automorphism data, as I said before, we impose this rigidity constraint, which, as we'll see, will limit the automorphism choices. Okay, so that's that. So what do we hope to do here, right? Well, what we can do is look at RT X over K E mod isomorphism. And it turns out that this is a group. So it forms a set, and then it has a group structure. It's a group. Encoded is not the right word to use here. It's a group with tensor product, if you will, as the group operation. Okay. So the structure on this thing is contravariantly functorial in T, which means that if I pick some T prime and T maps to T prime, then we get a map in the opposite direction. So you're welcome to verify that for yourself. It's pretty straightforward. You just follow your nose, as with most things of this type. And from this, we get the Picard functor. So the Picard functor, oh, and if it isn't clear, this is an abelian group. So it's let me say this. So it's an abelian group. It's important. Okay. So the Picard functor, there we go, is, I'll write it as pic X over KE, and it goes from K schemes to abelian groups. It sends a K scheme T, well, to this guy, so RT X over KE modulo isomorphism. And right, so I'll put that here. Okay, so that's what the Picard functor is, and our goal to construct the Picard scheme is going to show that, or is going to be to show that this is representable. So I'll note first of all that this guy here is actually independent of the base point E, and that's something that I give references for in the notes. It's again not so important for us, but know that it doesn't depend on E, and that Grothendieck provided more functorial constructions, or rather more natural constructions that don't reference E at all. So hopefully that's reassuring. You know, you might be thinking, since we have the notation pick here, that there's something to do with, you know, the usual Picard group, and that's true. So here's, in fact, go ahead.
Is there an op on scheme here? You mentioned something about contravariance earlier.
Contravariantly functorial. Yeah, hold on, let me think for a second.
Maybe not.
No, I think you're right. I believe there should be an op here. It shouldn't affect anything, but yeah, I think there should be an op there.
Sure.
Okay, so, right. What do I want to do here? Okay, yes. So basically, this is one way in which Picard schemes are actually, or Picard functors are defined, or the Picard scheme is defined in a lot of texts. So this is a nice concrete way of wrapping your hands around what the Picard scheme does, right? So basically what we can do is that we can take this category of rigidifications, mod isomorphism, and we can map it to what? Well, to the Picard group of x base changed to t, because again, the things that sit inside of here are line bundles on x sub t. And then we can quotient out by what? Well, we can take the schemes on, sorry, the line bundles on t and pull them back, like so. And it turns out, so what is this map, right? So what this map does is it takes the isomorphism class of a pair. Where does it send it? Well, it sends it to L, but of course that must be mod ft. Pull back the card group of T. And I guess if you like, this should maybe be an isomorphism class technically because it's a Picard group, but yeah, we won't be terribly precise about that. So this is, of course, a natural map, and this is a group isomorphism. And more than that, it's compatible with change of base point. So again, I said that if you change the base point, if you change the base point E, then you get the same thing, and you can verify that. And so the fact that the thing on the right here doesn't depend on the base point at all is maybe a sign that, you know, that's not crazy. Okay, cool. I really do wish, I'll keep writing here. I really do wish that you could display more of it on the same screen all at once, but yeah. Okay, so I mentioned that our goal is representability, and of course, the most important step, well, one of the important steps in proving representability is showing that what you have defines as a risky sheaf. So that's what we'll do here. So theorem. And I'm actually not going to prove the full extent of representability. I'm sort of going to punt after I do this, which this hopefully provides some justification or some peace of mind that we're not crazy. Okay, so this guy is a Zariski sheaf. And this is where the hypotheses we imposed on X will be important. Oops. Okay, so proof. What are we doing? So let's take T to be a K-scheme. And let's say that U sub I is a Zariski open cover of T. So then what we want to do is show that, so we need to show that a system of isomorphism classes which I will denote as this. Apologies for all of the nesting. And this will be iota sub I. Where, you know, what is this thing, right? Well, I guess, okay, I'm being somewhat sloppy here. So here's what I'm going to do. My apologies. Okay. Where this guy lives in what? Well, he lives in, I suppose, ui x over k e mod isomorphism. All right. We want to show that a system of isomorphism classes of, you know, rigidified line bundles that agree on overlaps. So agreeing on overlaps. Glue, and not just glue, but glue uniquely. I'm going to pan down a little bit. Okay. Oh, interesting. It undoes the pan. Huh. We want them to glue uniquely to, you know, some pair L iota restricting to each of our pairs. On UI, right? Okay. So if we paraphrase here, what we want to do is show that, so that is, if we have, so given isomorphisms, which look like, well, Li restricted to X base change to the intersection of Ui and Uj, mapping to Lj restricted to, again, X base change to Uij. You know, compatible with our rigidifications, extends to a globally defined rigidified line bundle. So this extends to let's say L iota. Okay. And really what this reduces to showing is that my pair here, L iota, has no non-trivial automorphisms, right? Because the automorphisms are exactly what you have to deal with when you try to glue. And those are the things that stand in the way of uniqueness. And so if you show that there are no such automorphisms, then you're golden. So, right, so what we want to do is say that. So I'll pan down like this. Okay, so I guess a claim. So has no non-trivial automorphisms. So then, of course, what we do is we let theta be an automorphism. So I'll just say be an auto. Okay. What do we want to do with it? Well, what we say to ourselves is that since it is an automorphism of L itself, it corresponds to an element. So theta corresponds to an invertible section in particular. So some element of gamma of what? Well, of And I guess what do I want to put here? I guess I can put this. Right. Okay. So that's good. So then one can show, and this rests in part on the hypotheses we placed, that ft, which remember is the base change of our structure morphism, so it's since xt to t, induces a natural isomorphism of the form take the trivial line bundle on T, or the structure morphism. Sorry, the structure sheaf. Thank you. Okay. It induces an isomorphism with the pullback of OXT. And so I guess, what do I want to say? Extending, although extending is not quite the right word, but extending to units. So it also defines an isomorphism of the units of both sides. So extending units. Restricting the units? You guys get the idea. Okay. So why does this matter? Well, if we pass to global sections, then what we have is global sections of T, OT cross are isomorphic to global sections of OXT on XT. All right. So what that means, to hopefully not be rambling too much here. So remember that I said that theta as an automorphism of L corresponded to an element here, right? Which means that it corresponds to multiplication by this section. So since that's the same as this right here, the global sections of OT cross, then what we have is this. So theta is multiplication by what? Well, it's multiplication by some u in gamma t OT cross. And if we think about it, this means that the pullback, let's say that the pullback of theta is also multiplication by u. But if we remember, right, so let's set up our diagram here. So we have the ET pullback of L, the ET pullback of L. Here's OT. So then this is the pullback of theta, right, which I'll say is multiplication by u, so I'll just put brackets on it to indicate multiplication. This is iota, and that's iota. Well, both iotas are isomorphisms, right? And I suppose the top guy is too, but what this means is that u equals 1. If this diagram is to commute, then u has to be 1. And what that indicates is that, you know, our automorphism was multiplication by 1, which means that it's the identity, which means that it's trivial. So hopefully that was not too confusing. I kind of rambled a little bit in places, but please stop me if you have questions.
I have one question.
Yes, what's up?
This like isomorphism where you pull back along FT, is
Where
that supposed to?
Yeah, go ahead.
Is that supposed to be a push forward?
Is this supposed to be a push forward? It is supposed to be a push forward, yes. Thank you.
Cool.
Yes, you're absolutely correct. Sorry. Other questions? Okay. So I'll note that this isomorphism here depends very crucially on the fact that we are geometrically connected and geometrically reduced. So, in particular, what this rests on is actually the global sections of X just being K itself. So if you want to work through that, then know that the hypotheses do matter. Okay. So cool. So this is hopefully some basic justification for why representability is a thing. And so then from this, we get the full theorem, which I will not prove, but there's a reference in the notes. And this is a theorem of a lot of people, which means that various people prove the result in various generalities. So we have Grothendieck, we have Ort and Nur, we have Artin. So then basically let X be as we said, right? So it's a proper geometrically connected, geometrically reduced, K-scheme with, and then, yeah, so the assumption that the assumption that we have a k-rational point, as I said before, is in some ways a bit artificial, but it's okay. So with E and X of K, okay. So then pick X over K E bar. So this is the Picard functor, is represented by a locally finite type. So remember before I said finite type is FT, LFT is locally finite type. K-scheme. Pick X over KE. And because E itself doesn't really matter, I mean, it will matter for bookkeeping purposes, but since it's independent of E, we'll say pick X over K. Okay. Cool. So, right. And again, there are a lot of things that could be said about this that I won't get to here. One thing that's important to note, of course, is that any group scheme over K is going to be separated. So if this functor, if the Picard functor is representable by a Picard scheme, then the Picard scheme is going to be a separated K scheme. Moreover, because this is a universal construction, right? So, I mean, it's representing a functor, so it satisfies a universal property, and that means that it's unique up to unique isomorphism via the standard argument that you're familiar with. All right, so now we've got our Picard functor. Cool. So let's use it a bit. So this gets us to our second section. Please stop me if you have questions.
Hey, Zach.
Yo, what's up?
Could you just explain how that uniqueness we just established before finished the proof of the theorem, the previous one? Like, how does that finish the proof of this theorem?
Right. So what we're trying to do is show that we can glue, right?
Yeah.
And that we can glue uniquely.
Mm-hmm.
Okay. So basically what we do is we look at overlaps, and we realize that on overlaps, the way that gluing works, right? Or basically like the obstruction to uniqueness of gluing on a particular, sorry, what am I trying to say here? So by restricting to an overlap, then you can transform, you can basically assume that the domain and the codomain are the same, what you're looking at, so you have an automorphism, right? Do you agree with that?
Mm-hmm.
Okay. So then we want to establish that there are no non-trivial automorphisms because, I mean, right, so here I sort of do a notation from before with the UIJs and so on, because if we can prove it on any open, then we should be good to go. It's sort of golden. Okay. So you agree with this reduction to the claim, right?
I guess no, that's where I'm stuck, but that's okay.
Well, so that's what I was just saying, right?
Mhm.
So we need to prove that we can glue up along overlaps, right? So if we restrict attention to a particular overlap, then we go from mapping from one line bundle to another, right? To instead, just a second. Right. So if you have multiple isomorphisms in play, right, then what you should be able to do is basically walk from Li to some Lj back to Li, not necessarily by the inverse of this isomorphism, but by a different datum that you have, right?
I see. Okay.
So by doing that, you restrict yourself to looking at an automorphism. And so then what you'd like to know is that, okay, well, we walked back to the same spot. So hopefully we got the identity, right? And if we did get the identity, then there was only one way to glue.
That's fair. So gluing is immediate, and that all you can do to like complicate uniqueness is compose whatever isomorphism you're given by some automorphism.
Yes.
Okay, cool. Thanks.
Yeah, thank you. I didn't maybe spell it out in the clearest way possible. So that's good. Okay. So so now we get to some applications, namely the theorems of the cube and the square. I'll say right now, I have a good understanding of why we talk about the cube, but I'm not exactly sure why the theorem of the square is called square. So if you know, then let me know when we get there. Okay, so again, we're interested in studying families of line bundles, right? So we already know from when we talked about rigidity that if some line bundle in the family has a particularly simple restriction to, let's say, a point in one of the factors, right? If you're thinking about you're thinking about your base as some kind of product, right? Because you're parameterizing by a scheme. Then things are nice, and we'd like to transfer over that kind of thinking, right? So particularly if we let's say, x and y be k schemes. Let's take y to be a k-rational point of big Y, and let's have L be, again, a family of line bundles on either x or y. It depends on you, but what we can say symmetrically is that it's a line bundle on the product. Just a quick note. So if at any point I ever omit subscripts or specs or things like that, then it's because I thought it was clear from context. If you are confused what's supposed to go there, you think something else should go there, just let me know and I'll clarify. Okay, so then let's have Ly be the restriction of L to X crossed with Y. Okay. And similarly, we can define Lx if we have a k-rational point of X. So, if you place various nice conditions on X and Y, then you might hope that the following is true. So one might hope what? Well, I guess I'll put this in quotes. So for nice, which receives single quotes, X and Y, and let's say we have some k-rational points X and Y with, I don't know, Lx, Ly trivial. Well, then L is trivial. That's what you might hope. But unfortunately, that's not true. And I can give an example illustrating that. Actually, a very nice example that has a lot of applications. It pops up a lot. So let's have E be an elliptic curve. So over K, and P here will be any K rational point. Okay. So then what we can do is we can look at the following restriction. So, or sorry, not the following restriction, we can look at the following bundle. So take the bundle that is, I guess, OE, but we twist by the divisor, which is given by taking the diagonal, and then take the pullback under projection of E, right? And recall now that, recall that E is a map from spec K to E. Okay. So then, why am I writing that? Sorry. Okay. I'll explain myself in just a second. Okay. So we're twisting our structure sheaf by this divisor, right? And this is a divisor that lives on what? Sorry, this does not live on E. This lives on E cross E. Okay. So on E cross E, we have the diagonal. Okay. We have the pullback of E, thinking of E as a point of E, if you will. Then, pulling back will definitely take us to the product, and the same thing, pulling back by the second projection. Okay, cool. So this thing, well, it has some familiar restrictions. So it restricts to what? Well, it restricts to, I don't even need to say it this way. Oh, E of, let's say, P minus E on both P cross E and E cross P. So if we plug in P equals E, then we get a trivial bundle, right? But if we plug in anything else, then we don't. And that's, a direct consequence of Riemann-Roch. So basically, this is a counterexample. Okay. So it doesn't work in pairs. What about triples? Right? What about triples? And the answer is yes. So that's where the following comes in. So I'll say it's theorem. Sure. I was going to say theorem of the cube, but we'll just do this. Theorem of the cube. All right. So we're going to have X, Y, and Z be K-schemes. So we're going to have X and Y proper. We'll have X and Z geometrically integral, finite type, and we'll have Y is geometrically connected and geometrically reduced. Yeah, okay. So again, the reason for many of these hypotheses is so that we can apply what we know about Picard schemes and representability of the Picard functor. So if you're curious, that's what's up. Okay, so then let L be a line bundle on the triple X cross Y cross Z. Okay, and so I guess okay. Let's give ourselves some K rational points. So we have an X naught, we have a Y naught, and we have a Z naught. So then let's assume that all of their restrictions are trivial. Then L is trivial. Okay. I can't keep the whole statement on the board, so I'm going to just do that. Hopefully that's not too egregious. So you have the hypotheses are omitted, but the assumption, I guess, is not. Okay. So proof. What do we want to do? Well, we know from our previous theorem, right, that pick y over k, y naught is represented. So it's representable, so in particular, it's represented by pick y over k, which I'll just write that way for simplicity. Okay. And what does that mean? Well, so the data of, oh, here we go, trivialization of the restriction of L to y naught, well, it's the same as what? Well, it's the same as a k-morphism. I'll call it F, from the remaining terms, X and Z, to the Picard group. Or Picard, sorry, not Picard group, the Picard scheme. Okay. This is just the universal property coming into play. All right. So then we claim that F vanishes, which gives that L is trivial. Because if you think about it, the class of, right. So the class of 0 in pick y over k, so the, right, so the, what am I thinking here? What's the right way to say this? So really, this should be interpreted as a statement that's happening perhaps on the functor of points, right? If this is vanishing, because this is a group scheme, you look at its functor of points that carries a group structure, we want to know that F is hitting the identity element no matter what scheme you feed in. So you can imagine that you don't need to look at all of them, you only need to look at some. But you know, if you're getting something trivial, then that should be corresponding to the class of the trivial line bundle. Okay, cool. So what we know is that LZ naught is trivial. So, what? Well, we can apply the universal property again, and what we know from that is that what I'll call FC naught, which goes from X cross C naught to pick Y over K, is trivial. Trivial, thank you. Right, so I apologize, I'm being a little sloppy about this. I'm kind of stumbling a bit. Okay, so what are we doing, right? We are trying to show that if we have these triple restrictions, if you will, so a triple of restrictions that vanish, then we want our guy L to be trivial. Okay, not vanish, they're trivial. All right. So we're going to use the universal property of our Picard scheme for Y, and we know that we have this kind of correspondence. So applying the same kind of reasoning down here shows that this restriction morphism is trivial. Okay. Cool. So why should that matter? Well, if you notice, this looks a lot like the setup in which we applied rigidity, right? Or the rigidity theorem, and that's exactly right. So by the rigidity theorem, that's not how you spell rigidity. We have a commutative diagram, right? Which looks like X crossed with Z, and then here's the Picard group, right? What's this map down here? Well, this is F, okay. Here's Z, restricting via projection, or mapping via projection, sorry. And we get a unique morphism here, G. So, you know, that's really good because now the map G is a lot simpler, but what we can note is the following, right? But Lx naught is trivial. What does that mean? Well, that implies that Fx naught, the restriction from x naught crossed with Z to the Picard group, vanishes. But this morphism is really nothing more than G. So this is the G vanishes, which means that F vanishes, and we're good. Okay. So we're almost done with this section, and then I think I will put in a break before we wrap things up. And in fact, I may not get to the end of this section before I put a break in. So let's go to the consequence of this. I guess first I'll ask: are there any questions?
Can you say again why F being trivial will give us that like this total line bundle L is trivial?
Yeah. So okay. So right. So we have our Picard scheme here, right? Pick y over k representing this guy, and okay. So what do I really want to say here? And let me think for a second. So what I think I really want to say is that okay, yeah. Cool. So what is the data of a morphism into pick y over k, right? So the data of a morphism is, well, exactly provided by, this is the same thing. Maybe I should write this down. Let me try to do that. I will write in red so that it's different, and I'll scroll up. Right, so the data of F, we'll just say, corresponds to give me something in there, right? And this is the same thing as what? R of X cross Y cross Z. Shoot. Sorry. Okay. So I'm being really sloppy here. Let me say this one more time. Okay. So we identify the data of F with an element of this. So it's an element of that, right? And an element of that is the same thing as a line bundle, or rather the isomorphism class of a line bundle on X cross Y cross Z, right? Because it's the same thing as x cross z base changed to y. With the rigidification, but what's the rigidification? Well, the rigidification, so it's a line bundle L, with Ly naught, right? The pullback by that section is the same thing as the restriction, mapping isomorphically to, I guess, whatever the trivial bundle would be. So this would be on x cross z. Does that make sense? Do you get what I'm saying?
I think almost.
So remember, yeah, this is a confusing point. I confused myself about this too. Yeah, so let me scroll back up to how the rigidification stuff is even defined, right? So we're pulling back by the section induced by the identity morphism, right? Where the identity morphism is encoding our group structure. So in the case of our case schemes, right? Sorry, we have a k-rational point. In the case of abelian varieties, it plays the role of the identity, but that doesn't matter here. The point is that we have this k-rational point, and what we do is we pull back by it. Well, pulling back by this thing is the same thing as, in the case that we're in, where we're working on a product, it's the same thing as restricting to that point, or rather to the stuff crossed with that point. Like that's exactly what the pullback amounts to. So that's precisely why these two things are the same. So like this data of, this is the rigidification right here. So we basically I basically said that, yeah, providing you the rigidification is the same thing as giving you this morphism. And so because of consistency type stuff, right? This was data corresponding to L. So the information that's over here, a priori, I mean, it could correspond to a different line bundle, but it also needs to correspond to L. I realize it's maybe a little sloppy, but.
Okay, so the point is that like base changing y to x by z is just considering this triple product.
Yes, exactly.
And then saying that it's like trivial at this point y naught is saying that like when you restrict y naught cross x by z, then you get the trivial bundle.
Yes.
Okay, this is making sense.
Yeah. Sorry about that.
Well, now it's all good. Thanks.
Okay. And actually, I think that's probably a good place to take a break. So let's resume at 11:10. And then if anybody has questions or whatever, feel free to ask me right now. I think that's probably the best way to go. You know, and I definitely won't go over 12. So like if I don't cover this stuff that I want to cover, then I will just briefly recap next lecture and we'll start where we left off. Don't worry about that. I won't marathon. for anyone who cares, there is a small technical point I should note, which is that it was important from the purposes of the rigidity theorem that we met a variety of hypotheses. That's what some of the conditions up here are doing for us. It's also important to note that this guy is actually locally finite type and separated. Because if you look back at the rigidity theorem, we needed those kinds of conditions to actually apply this kind of reasoning. So, you know, it is important that we know a little bit about the structure of this guy and not just, you know, not just the universal mapping property. Okay, so I'm going to go ahead and get started again. So what we just proved is the theorem of the cube, which very simply says that if I have a line bundle defined on the triple with some nice conditions on the things I'm actually producting together, then if I have a restriction to each piece being trivial, then the whole thing's trivial. Okay, so why does that kind of thing matter? Well, for one, it simplifies a lot of arguments. So in particular, it allows us to deduce something called the theorem of the square. It's a little confusing because there are two results that often go by that name, but I will follow the convention of Brian and Conrad and do it the following way. So corollary, and I think I'll leave this one as a computation. It's not complicated at all. It's actually very straightforward and somewhat fun. So let's have A over K be Abelian variety, and let's have T be a K scheme. Okay, and let's pick a triple of points, where these will all be T rational points of A, or T points, maybe not, I shouldn't say T rational, I keep saying that. And let's have L be a line bundle on A. Okay, so then L of A1, A2, A3 defined by the following monster equation, but it's not anything complicated, it's just long. So what you do is, again, because we have a group scheme, then we can add up our rational points. So if we add up the triple of points and pull back L, and then tensor up with all the pairwise sums, applied to the inverses, and then we look at the pullbacks by individual pieces applied to L, not L inverse. And finally, tensor with, so, okay, let me not write the last piece so far. So we have this line bundle here defined by, you know, add up the triple and then basically subtract off the pairwise sums and then add in the singular pieces, if you will, or what, taking them one at a time. So the claim is that this is trivial, which means that since everything is taking place on T, that this is the structure sheaf O sub T. But we can do a little bit better. It's not terribly important, but it is nice in a lot of cases to know this. If we tensor on one more piece, which is trivial, this is pull back L by the identity section, and then base change to T and take the inverse, then not only is it trivial, it's trivial canonically. as I said, I'm going to leave the proof as a sort of exercise. Again, it's a fun little result. My hint is that you should reduce to thinking about basically a triple. So the product of A 3 times, and these maps are projection maps. That should help simplify your life a lot. Okay. Cool. And I'm actually going to move that off screen. Cool. All right. So this is great because it tells us about the theorem of the square. So the theorem of the cube, it was clear why we're talking about a cube is because we had 3 things. Why this is called the theorem of the square is not exactly clear to me, but such is life. So let A over K be a variety. There we go. Okay. L is a line bundle on A. T is the K scheme. And let's have X and Y be T points. Ooh. Okay. T points of A. All right. So then there's a natural isomorphism, and here's what it's going to look like. So recall that we had a translation morphism that we defined for T points of A. And in particular, this morphism was defined on A base change to D. So we can take the sum of our points and pull back by translation by that on the base change of L. Okay. Tensor up with, well, L. Geez. That's isomorphic to what? Well, it turns out it's isomorphic to Tx, pullback of L, tensor with Ty pullback of L. And then there's the correction term that we need to introduce, so I will do so. So you can take the product of these 2 guys, pull back. Oh, I actually need to put this on the next line, so I'm going to select this thing. I don't know why I'm doing this the hard way. We'll put it here. Okay, there we go. So we take the product, we pull back of by, sorry, we're going to pull back by the product of this thing, lambda of L, which I will define in a second. Then we tensor up with E, pull back L. And this whole thing has to be base changed to A sub T. Okay, what the heck is going on? Well, okay, first of all, everything that's here is going to be a line bundle in A sub T. Hopefully that's clear. All right, what are the terms here? So the first thing I'll write down is that gamma L is by definition the pullback by multiplication tensored with the pullback by the first projection tensored by the pullback of the second projection. And this is a line bundle on the product. Okay, it has a name. It's called the Mumford bundle. And it's very important for understanding the structure of dual abelian varieties, as we will maybe not fully see today, but that's okay. All right, so we don't need the first line, but I'll keep this stuff. All right, so we got that. how is L sub A sub T defined? Well, L sub A sub T is by definition the pullback by P, sorry, of L. For P, the projection morphism, which looks like project AT onto A. All right, cool. So the reason why we introduce these terms here is that what we're really doing is translating the previous result, right? So if you recall, we have our triple sum, we have our pairwise sums, we have our singular things, and then we have this piece. Well, unsurprisingly, this piece is going to be contributing to this little bit here at the end. So we can, of course, ignore it because E here, right, is mapping from spec K into our abelian variety. If you pull back, you're going to get a line bundle on spec K, which is necessarily trivial. So from sort of canonical isomorphism perspective, we want this piece here, and it does make the theory nice in some ways, but you can ignore it for most purposes. Okay, so that term is sort of gone, and similarly, we could eliminate this piece from this side. What about the other things that are going on? Well, really, this is about determining what the A1, the A2, and the A3 are in the previous result and applying that, if that makes sense. Hopefully it will be. So I'll just say proof, and this is more of a sketch, but I guess what we can do is take, let's say A1 is P, and then let's take A2 to be what I'll call CX and A3 to be CY. So what is CX? What's CY? Well, CX is just what's this? So you have AT maps to T, so project in the opposite direction, and this maps to A by our rational point. Composition is basically this constant map CX. Okay, this is the constant map, right? And what I invite you to do is basically explicitly write down what adding up these rational points gives you as maps, and you should see that the result we want falls right out of the previous theorem, pretty much verbatim. So I'll leave it at that. Hopefully that's satisfactory. If not, let me know. Okay, so what does this tell us? Well, in particular, if we, again, ignore the terms that are sort of correction factors, if you will, then we get a non-canonical isomorphism that looks like this. So we have sum up your points and pull back, and this will be this guy here. Tensor up, and that's isomorphic to what? Well, it's isomorphic to this. What if we rearrange terms here, right? What it says is this. That if we take this guy and we tensor not with L of AT, but L of AT inverse, I don't need to print the C here, then what that's isomorphic to is the TX pullback of LAT tensored with the TY pullback of LAT and aha, this looks like a group structure. And it is, right? This looks like a homomorphism property. So that's exactly correct, corollary. again, we have A are abelian varieties, so I won't write that again. What we know is that phi sub L, which maps from A to, in this case, the Picard group of A over K, given by what? Well, given by X maps to, geez. Tx polar of L, tensor with L inverse, is a morphism of group schemes. Cool. So usual caveats apply, right? We really understand the Picard scheme in terms of its functor of points anyway. Same way we want to think about the functor of points of A. So really you should view this as a statement, this is a perfectly fine statement if interpreted correctly. So this left-hand side is perfectly fine. And then this should be interpreted as happening on the level of the functor of points. So then what you do is you replace X not by a point of A, but by a T point of A, and you replace L by L base change to A sub T. But the point is that this depends on L, and that it is a morphism of group schemes. So this morphism is super important. I don't know if it has a name in and of itself. I'm just going to call it phi sub L. But yeah, it should be hopefully clear from the previous corollary that this is, this statement right here basically says that this thing is a homomorphism. I'll note that, you know, when we talk about the functor of points of this guy, we're actually looking at isomorphism classes. So really you should maybe write the isomorphism class on this side, but we're not going to do that. Things would get very cumbersome very quickly. Okay, cool. So please stop me if you have any questions. Okay, cool. So that's a fair bit about families of abelian varieties. So in the remaining time that I have, I'm going to try to sketch a little bit about how we think about duals, but I probably won't get to showing that the dual is an abelian variety, and that's okay. So here we go. So line bundles and duals. So from the previous section, right, we know about pic sub x, or yeah, pic sub x over k, or you know, pic sub x over k comma e with the distinguished rational point. We can associate to that this guy, right, which I said was a nicely behaved, or rather, if I have any group scheme over K, I can think about G naught, right? If this is G, then G naught is, of course, the scheme associated to the connected component of the identity. It has a lot of nice properties, and in particular, if A is an abelian variety over K, then what we get is pic A over K, and E here will be the identity, of course. This thing has a name. This is the dual of A. And we will see, you know, that the dual actually is an abelian variety in due time. Note that this notation seems a bit overloaded because we already know about a notion of pic 0. And it turns out, and this is spelled out in the notes in an exercise, that this overloading of notation is not an accident. So this actually does bear a very close relationship to pic 0. So Yeah. All right. So how can we use this kind of stuff to our advantage? Well, let's have y be the Picard group of x over k. Again, where x has all the hypotheses on it to make it nice. Then what we can say is that the Picard group, sorry, the Picard functor applied to y, right? So if I apply a functor to its representing object, this is often a very important invariant of sorts. I mean, you get a universal type thing, which tells you a lot about the functor. So this guy corresponds to some isomorphism class, which I'll call UXIX. Again, it depends on x. And the representing pair here, representing in the sense of isomorphism class, this is the universal rigidified line bundle. Over x, if you like. Why is it universal? Well, because it encodes data via pullback, right? So what we want to say is that, of course, by definition, UX is a line bundle on x times y, which you can think of as x sub y equivalently. And iota x is a rigidification, so it's going to map the pullback by this section, this induced section, I guess, to the structure sheaf. That should not be an OXY, that should be an OY. Cool. And, right, so why does this matter? Well, so if I give you any K-scheme and any rigidified line bundle Li on XT, then, so given these things, there's a unique K-morphism, so I'll just say phi from T to Y with a nice property. And what property is that? Well, it's that L iota should be obtained from our pair UX iota X via what? Via pullback, right? How do we pull back appropriately? Well, we pull back by identity X crossed with phi. Where I'm being a little sloppy here, saying that I have a pair and I pull back, then I'm going to pull back both things in the pair. Okay. So, all these constructions are sort of up to rigidification. So, you do need to keep track of rigidification, but I'm not going to do that super precisely. Again, you could check the notes if you want to be careful about the bookkeeping. So if we're in the case of an abelian variety, then we can restrict our guy. So we can restrict our universal rigidified line bundle. So I'll say U sub A iota sub A to what? Well, we can restrict it to A crossed with A dual. And this is because A dual, of course, sits inside of the Picard group of A over K. And what we get is the Poincaré bundle. Not exactly sure why it has the name Poincaré bundle. I mean, I figure Poincaré did work relating to it, but I'm not particularly savvy on the history there. Okay. So again, there's some rigidification things that one has to worry about. the Poincare bundle needs to satisfy a couple of properties, but I'm going to sweep that under the rug. Okay. So basically, in order to effectively understand the dual, in fact, give this a name, not in red, but in black, P for Poincare. Okay. In order to understand a dual, right, we only understood the Picard scheme in terms of its functor of points. Similarly, we really understand the dual only in terms of its functor of points. So what we want to know is, if I have a morphism into the Picard scheme, right, then when does it factor through the dual? Because if we can understand that, then we can understand a lot more about the dual itself. And a good way to understand this is to say that a morphism, so let me think here. Okay, in my notes, I've overloaded Y perhaps. So we're going to use T, I guess. Hold on. Let's use T. Okay, so I'm going to eliminate this, all right? So I have T is mapping from, sorry, we have a morphism like this, right? So, and down here we have a dual, which maps in here. The question is, when do we factor, right? And the claim is that this holds if and only if well, this morphism, so this guy here, sorry, this corresponds to a line bundle L on A crossed with the Picard group. That doesn't sound right. Hold on. Sorry. This should be a line bundle on AT, right? Because you take the Picard group, sorry. So the T points of the Picard group of A, sorry, the Picard scheme of A, is exactly saying, look at rigidified line bundles on A sub T. Okay, so we're going to look at a rigidified line bundle on A sub T, and that line bundle encodes some important data, right? So what we can say to ourselves is that we want L to be PR2 trivialized. Okay, what does that mean? Well, we have this guy, if you will, our Poincare bundle data. And what we can do is pull it back. And restrict to what in particular? Well, to the second factor, right? So, hold on. I realize that I'm sort of, I imagine people are probably spacing out because we've been at this for a while. So let me try to rekindle some energy here, right? What are we trying to do? So we're trying to understand when things factor through the dual, okay? And we understand that there's this sort of mapping property that is satisfied by the universal line bundle, or the universal rigidified line bundle. The Poincare bundle, which we hope to capture similar data for the dual, in which case, in fact, it will. That hope is not hopeless. It's going to play a role, and what role does it play? Well, the factoring happens if, when we look at the line bundle that corresponds to our morphism here, T to the Picard scheme, then when we basically restrict it to the second factor being constant, right? So you can imagine cycling through different T's, right? If L is defined in A sub T, you think of this as A cross T. By restricting to individual T and T, and each time you get a trivial line bundle, then, right, so what am I doing? Okay, I see. So that is one way to think about it, but let me phrase it a little bit differently. So what do we want to get, right? So we want a compatible family, right? So this is a compatible family of restrictions or trivializations, if you will, of Ly to O sub A, where Y is some point in Y of K. So this should be not Y, but T. Yeah. Okay. Sorry about that, guys. So what I said before is true. You want to restrict to individual points of T, but how do you get those points of T? Well, you should get them by, you should get these trivializations as pullback. So induced by pulling back our Poincare bundle and restricting. Shoot. All right. So where does this come into play, right? Well, the place where this comes into play is the following claim, which I will not prove because it's just a computation. But phi L, which recall maps from A to the Picard group of A over K, factors through a dual. Okay, so let me not do more today. I can feel myself drifting a little bit, and I fear that the same is probably true for you guys. So let me hope, or let me try to package together what we've done and point you in the direction of what we're doing in the future, which will hopefully be a little bit less technical. Okay, so ultimately, what we hope to do with this dual, right, is understand the structure of A itself. Because it turns out that the dual captures a lot of really useful information about A. Turns out that they're equivalent in the sense that they're isogenous. So it's important that we build up the machinery to actually understand what the dual looks like. So, we sort of abstractly define the dual by talking about Picard functors and Picard schemes. We proved that the Picard scheme itself, we basically proved that this phi L map associated to our line bundle A carries a kind of group scheme structure, or rather it's a group scheme morphism. And then we want to use that map phi L to actually understand the dual. And so then we did a little bit of, I think, sort of badly presented technical stuff to show when we factor through the dual. And the claim is that this map phi L, which we care about, factors through the dual. And so then why does this sort of thing matter? Well, this sort of thing matters because A, it helps us wrap our hands around the dual a lot easier, but also, or I guess sort of an extension of that, it gives you ways to concretely understand the points of the dual, right? So, later on in the notes, and you can check this out for yourself, these kinds of results allow you to say that, oh, we know, like, so we can say precisely, for example, what a dual of k bar, the k bar points, looks like. And, hint, it corresponds to degree 0 line bundles in a very nice way. So I think I'm going to leave it there for today. Again, I apologize if it got a little spacey at some points, but yes, we will pick up from here tomorrow, and yeah. So I'll stick around. If you have questions, please let me know.